Now we move to chapter 9 and do some of the exercises in that chapter. If you look at the slide, in chapter 9, we are going to cover section 9.1, 9.3, 9.4, and 9.5. Section 9.1 is talking about limit. This chapter is basically introduction to calculus. And then as we go to 9.3, 4, and 5, we get into equation of tangent line and then derivatives and the rules of derivatives for 9.3, 9.4, and 9.5. And you have the list of the problems we're going to do in this chapter. First, in section 9.1, we're going to do number 30. Number 30 says, find the indicated limit. It is asking you to find the limit of this function, the limit of, parentheses, 4x to the fifth minus 20x squared plus 2x plus 1 as x approaches 0. The logic you use, for example, in this first part, you say you have an x here which is to the fifth power. As x gets smaller and smaller and get closer and closer to 0, this would ultimately come to be 0 to the fifth power, which is 0, and 0 times 4 would be 0. Therefore, this whole term would approach 0. The same logic for this term, the same logic for this term. So everything with x here would approach 0. Therefore, the limit of this function would be equal to 1. Another way you look at it, you write this as equal to 4 times 0 to the fifth power minus 20 times 0 to the second power plus 2 times 0 plus 1. As you can see, everything here would be 0 and 0 and 0. Therefore, the limit of that function as x approaches 0 would be equal to 1. That's done. That's problem number 30. Let's do another problem and see whether that would be any different. Problem number 40, again it says, find the indicated limit. Problem looks a little bit different than this one. It's actually in the form of a quotient. Problem number 40. It says find the limit of x times square root of x squared plus 7, h squared plus 7, divided by 2x minus square root of 2x plus 3. This as x approaches 3. You can basically solve this problem the same way you have solved the previous problem. You would say as x approaches toward 3, then this limit would be equal to 3 times square root of 3 squared plus 7 divided by 2 times 3 minus square root of x is 3. X is approaching 3. So 2 times 3 plus 3. So this would be equal to 3 times square root of 3 squared is 9 plus 7 divided by 2 times 3 is 6 minus square root of 2 times 3 is 6 plus 3. Therefore, equal to, the numerator would be 3 square root of 16. Denominator would be 6 minus square root of 9. Therefore, 3 square root of 16 is 4. 6 minus square root of 9 is 3. So you would have 12 divided by 3, which is equal to 4. And that is the answer. So as this function, as x in this function approaches 3, the value of the function itself approaches 4. The other problem we wanted to do was problem number 58. I'm going to see why 58 would be different in just a second. Problem number 58, again in section 9.1. It says find the limit of z to the third minus 8 divided by z minus 2 as z approaches 2. One thing you would notice, if you just go ahead, like in the previous examples, if you go ahead and substitute for z here and here, substitute for z2, you're going to have 0 in the denominator and 0 in the numerator. So you would have 0 divided by 0, which is basically undefined. So one of the things you would notice is that the numerator you can factor out. So anytime you have a quotient in particular, it will come into play. Every time you have quotient machine, you can simplify. You have to simplify it before you substitute the value that you have, in this case 2. So let's see what happened. This would be therefore equal to finding the limit as z approaches 2. The numerator, z squared minus 8, can be factored as z minus 2 times z squared, if you remember your special product rule, plus 2z plus 4. Okay? That's the numerator. And denominator is z minus 2. So you can see now it can be simplified because z minus 2 in the denominator and z minus 2 in the numerator would cancel. So this problem is now reduced to finding the limit as z approaches 2 of, there's actually no equal sign here. Let me just get as z approaches 2 of z squared plus 2z plus 4. Now you can substitute. For z, you substitute 2. So it would be 2 squared minus plus 2 times 2 plus 4. Therefore, this limit would be equal to 2 squared is 4. 2 times 2 is 4 plus 4 equal to 12. So that's what the limit. So when you have quotient, like in this case, first you have to identify whether you can factor out and make it simpler. And that normally comes into play because when you substitute for z2, you're going to end up with 0 either in numerator or denominator, or in both cases, such as this example, you will end up 0 divided by 0. So that's what That's what you don't want. Let's go to another problem, an application problem. This is an interesting problem. Number 82. Number 82. It says the population of a certain breed of rabbits introduced into an isolated island is given by PT, that's the population of rabbit, equal to 72 divided by 9 minus t, when t is between 0 and 9. So just write this number 82, population of rabbit as a function of time, t is time in this case, equal to 72 divided by 9 minus t, as t is between greater than or equal to 0 and less than 9. And it tells you where t is measured in months. A, find the number of rabbits present in the island initially at t equal to 0. At t equal to 0. So you're evaluating this function at 0. That would be equal to 72 divided by 9 minus 0. That would be equal to 72 divided by 9 equal to 8. So initially there are 8 rabbits on the island. Then B says, show that the population of rabbits is increasing without bound. The population of rabbits is increasing without bound. Then you have to say that as t approaches, now you're trying to find the limit of pt as t approaches 9. So that would be equal to 72 divided by 9 minus 9. So what you would have here is 72 divided by 0, which is basically infinity. So as t approaches 9, the population of rabbits approaches infinity. In part C, it says, sketch the graph of the function. Sketch the graph of the function. Well, that is simple. You would have p of t on the vertical axis. You have t on the horizontal axis. T goes from 0 to 10. As you can see, if you, in your function, which is right here, if you evaluate the function from t equal to 0 and increase t by 1 every time t equals 0, we know you start at 8. And then t equals 1, it would be 72 divided by 8. T equals 2 would be 72 divided by 7, and so on and so forth. And as t goes toward 9, which is right here, this is the limit. As t goes toward 9, all of a sudden, when you start from right here, which was only 8 rabbits, as you approach, it goes up slightly at the beginning, but all of a sudden, as you approach 9, it's going to explode. It's going to go up that way. If you have a graphic calculator, you can graph this very neatly. Let me, I put this on the blackboard as one of my favorite sites. Let me see if I can find it. There it is, coolmath.com, online graphic calculator. you have a graphic calculator right in front of you. Very simple. So if I want to graph this function, which problem number 82, PT, which is on the left-hand side, your y-axis, you don't type that in, but it is equal to 72 divided by 9 minus t. So you put 72 divided by 9 minus t, you put it in parentheses. 9 minus, well, t is your variable, so you can put x. Actually, you don't have t, but x is the variable on the right-hand side, or your independent variable. Close the parentheses. Okay, so all you do is you put in your right-hand side of the parentheses, so you can see it in this box, and push evaluate. That will graph it. There is the graph. Actually, this one is showing it will start, if you count this, here is 0, 1, 2, 3, 4, 5, 6, 7, 8. And we know that when x was 0, the value was 8. To see a little bit better, because as this one goes toward 9, that should go toward infinity. So we are having this at x minimum. Let's make that x minimum of 0, and x maximum, you want that to be 10. That is okay. And the y minimum, I keep it at minus 10. Y maximum, we want to keep it, a large number, at 10,000. Okay. And now you zoom out. This part, see, this is when y is negative, but this is the part you're looking at. So we'll graph it for you. That was problem number 82, and I think that's the last problem in section 9.1 we're going to do.